cloud. Right, good evening, everyone. My apologies for that, but it's frustrating when the system changes the buttons in front of you without you doing anything. So, but there we go. So welcome, everyone. I see that we have 28 participants. As I said, I will just apply mute all. And Gemma, you'll be able to unmute yourself. I'll be able.
Yeah.
Yes, well done. Thank you. Okay, right. Very pleased to see everybody, and especially to our speaker this evening, which is who is Dr. Gemma Richardson. Dr. Richardson took her undergraduate, master's and PhD degree at the University of Liverpool, both in geophysics, and she's now a specialist in geomagnetic hazards with the geomagnetism team at the British Geological Survey, not Society, which I got wrong in the first case, up in Edinburgh. So her current projects and collaborations include participation in the SWIMR project, that's SWIMMR project, which is about improving the UK's capabilities in space weather monitoring. Euphoria, which I won't try to spell that out, but it's nothing as it should be, as it were, but which addresses the impacts and mitigation of solar eruptions at a European level. And also investigating the impact of space weather on New Zealand's infrastructure. So she lists walking and mountain climbing as personal interests. So I hope she gets the opportunity to do some of that in the Southern Hemisphere. As well as being a bit of a whiz on the programming side, she is also a fellow of the Royal Astronomical Society and a STEM ambassador. So very welcome to you, Gemma, and look forward to the following talk. Thank you very much.
Okay, well, cool. Thank you very much for that. Having said that, I had the option to share screen. It now says that you've disabled it.
Oh, I have not.
So you might need to give me permission. Apologies, I should have tried that before.
Okay, so we'll try that. Does that look good?
Yes, I think so. There we go. Hopefully.
Yes, excellent, excellent.
Great. Well, thank you very much for the introduction. I should say that anything I say today has probably been done not just by myself, but also by other colleagues in the geomagnetism team. And I'll talk to you today about the kind of environmental conditions in near Earth space, or space weather, as it's more often referred to. Now, I can understand that maybe a few of you might be thinking, why does a geological survey study space weather? What's that really got to do with geology? But hopefully by the end of the talk, it will become a bit more obvious. So just to start, I thought I'd give you just a quick overview of what I'm going to talk about. So firstly, I thought I'd give a quick introduction to space weather. I realise some of you are probably quite familiar with it, but I'll just go through kind of space weather from kind of my point of view, and particularly the impacts that I'm interested in. So I'll talk a little bit about the research into effects on grounded technology and the bits of space weather that are most relevant for that. And then I'll talk a little bit about forecasting and space weather services that we do at the British Geological Survey. So what is space weather? So in its simplest form, it is just a term that says what are the conditions in space near the Earth. More specifically, it's generally used to refer to conditions that would have an impact on technology, infrastructure, or people, either in space or on the ground. So there's this nice graphic from the European Space Agency which explains kind of a lot of the hazards of space weather. So although on this diagram we've got cosmic rays and energetic radiation belt particles, which are classed as space weather, but the vast majority of space weather, particularly that we kind of are really interested in, comes from the sun. The sun very much controls the space weather we see at the Earth. And that comes in many forms. So the sun is responsible for releases of solar energetic protons, solar flare radiation, and coronal mass ejections, which I'll talk a little bit more about shortly. And that has lots of different effects on the Earth. So as you would imagine, space weather very much affects satellites because they are up in space and they're bearing the brunt of it. So things like solar energetic protons and solar flare radiation particularly can cause radiation damage and solar cell degradation on satellites, so shortening the life of the satellite. And then there are also these things called single event upsets. So they're caused by some of these charged particles that have been released from the sun that get through the shielding on the satellite and go through the body of the satellite. And a lot of the time that's not a problem, but sometimes what happens is they hit particular bits of circuitry inside the satellite, and that can cause issues either because it causes a electrical signal, so it maybe tells the satellite to do something that the controllers on the ground haven't told it to do, and that's awkward, or it can actually cause damage as well, or certainly interference on whatever the satellite's up there to measure. So that's an issue for satellite operators, because obviously you can't just nip up and fix something on a satellite. So understanding space weather and where they need to maybe do something slightly different with a satellite to protect it is important. If we then move down into the atmosphere a little bit, into this region called the ionosphere, which is a region of the atmosphere around 110 kilometers upwards, then space weather can cause currents in the ionosphere, like electrical currents and other disturbances, which again have an impact on satellites because it disturbs the signal coming from the satellite to the ground. It also causes, say, navigation errors if one of your satellites is actually a GPS satellite or a GNSS satellite. For most of us, the main use of sat-nav is in our cars, and that's not going to be a problem from space weather because your sat-nav's not actually very accurate. But there are certain industries that use very high precision satellite navigation, like down to centimeters or even less. And for those cases, if you had some kind of space weather event, either particularly a geomagnetic storm, then those signals are going to be disturbed and your accuracy is going to go way down. So it's really important to know that's happening and to understand what impact that's going to have on whatever your application is, whether it's using GNSS timing or precise navigation or anything like that. Sticking with the theme of navigation, directional drilling is something else that can be affected by geomagnetic activity. So oil rigs like this, when they're drilling their well paths underground, they need to know where that's going. And one of the cheapest and easiest ways to navigate your drill underground is to use the magnetic field as a map, which is fine on a quiet day, but if you have a big geomagnetic storm going on making lots of magnetic variations, then whatever you measure is not necessarily going to be caused by the rocks around you, it's going to be caused by the space weather. So it's massively important that they know if there's lots of activity that they can't trust the measurements and then have to use other systems for navigation. Aviation is another industry that can be quite affected by space weather. So again, it can be prone to these kind of single event upsets, generally not in a kind of catastrophic way, but it might cause, say, a light to come on in a cockpit that shouldn't be on and things like that, which are disconcerting and not ideal. And the other issue for aeroplanes is exposure to radiation. So again, there are things that airlines can do to make sure that they don't expose people or the crew to excess radiation during a space weather event. So moving down a little bit further, space weather also has a big effect on high frequency radio waves. So again, it can really disturb your communications. And then if we move down to the ground, there's these induced geoelectric fields and currents that can be induced in the ground, and then they can flow into technology systems like power grids, pipelines and communication cables and railways and all those kind of things. And it's kind of this bit down on the ground that I'm most interested in. So just to explain a little bit further, so as I said, space weather is mostly controlled by the sun, and mostly it's to do with this, what we call this solar wind. So the solar wind is just a continuous stream of charged particles from the sun, and that heads out obviously in all directions from the sun, and then when it hits the Earth's magnetic field, first it controls the shape of the magnetic field. So if you imagine, you know, back to being at school with your bar magnet and you put iron filings over it, the lines are all very symmetrical. But because the Earth's magnetic field, although it is mostly dipolar like a bar magnet, because it's being buffeted by this solar wind all the time, it gets squashed on one side, or the side next to the sun, and on the other side it gets stretched right out into space like a kind of teardrop on its side. And that solar wind is quite variable in terms of density, speed and temperature, and it contains some of the sun's magnetic field, and then every so often you get big disturbances in that solar wind that cause these kind of so-called space weather events at Earth. So in terms of the events that affect the ground, there are kind of two main disturbances. So one is from coronal holes and the other is coronal mass ejections. So coronal holes, so this kind of big blue patch on the image to the right is a coronal hole. So they appear dark when we look at the sun under most kind of different wavelengths of light. And they're dark because they're a little bit colder and a little bit lower density than the rest of the plasma around them in the corona. And they also have what's called open magnetic field lines. So rather than the magnetic field looping back and connecting back on the surface of the sun, those magnetic field lines are open to space. And what that means is that high-speed solar wind streams can escape out into space where the speed is about double what it normally is. And if you have a patch of solar wind that's really fast, then when that hits the Earth's magnetic field, that obviously has an impact. And just to complicate things a little bit further, because it's a 3D system and everything's rotating, the Earth's solar wind, the sun's solar wind doesn't actually go in a straight line between the sun and the Earth. It gets kind of curved and twisted as we go. So if you put a fast patch of solar wind into that, you also get a compression region where it hits the solar wind ahead, the slow solar wind ahead of it. So then when that sweeps past the Earth, we get both faster solar winds, but also just more complication just because of that whole rotating system. So that can lead to kind of moderate sized geomagnetic storms. The kind of bigger impact in terms of getting really big geomagnetic storms come from these coronal mass ejections. So I'll play a video in a moment just to actually show you one, but just to explain what we're looking at here. So this is what's called a coronagraph. So this is an image from a satellite where this kind of disk of solid color in the middle is called an occulting disk. So that is basically, it's pretty much a fake eclipse. So that disk blocks out the light of the sun itself so that we can see the corona. So much like when you get an eclipse and the moon blocks the sun and we can see the corona, which is a bit like the sun's atmosphere kind of stretching out from the sun. This is just an artificial way of doing it from a satellite. So if I play this video, you'll see a coronal mass ejection released on this side of the sun. So there we go. So hopefully you can see that. What I will just do is, there we go. So that's what the coronal mass ejection is. So basically, it's a huge release of plasma and some of the sun's magnetic field and charged particles all being released out away from the sun, and it expands as it moves out into space. So this is the view from the side. If we then look at the view, this is a different view, but from a slightly a camera with a slightly wider field of view on a different day. And it's a bit blink if you miss it, blink and you miss it, but I'll just play that again. So this one is, there we go. This is what we call a full halo CME. So a full halo means basically that it just goes all the way around the sun. And that can mean one of two things. It either means that you're looking directly into a coronal mass ejection that's heading straight for you, or it means you're looking at one that's heading straight away from you. In this case, we were very sure it was heading towards us because of what followed. So if I let it go on a bit further, which is all of this. So these, every little spot here is a charged particle smashing into the camera. So kind of going back to that original slide about different impacts on satellites, you can see that after a while, this is going to start to have an impact and it's going to degrade your instrument. This camera does actually recover after this event, but you know, every time you have one of these events and it gets bombarded with these particles, you're going to start to maybe lose some of your definition in your video. That's just a slight aside on charged particles. Okay, so coronal mass ejections are usually associated with one of two things, either solar filament eruptions or solar flares. So a filament is this kind of dark line here, just to the right of the center of the sun. And filaments are a cloud of kind of charged gas that are suspended above the surface of the sun. And they're kind of held in place by regions of different magnetic polarity either side of it. But because they're controlled by magnetic forces, they're inherently unstable. So they'll sit on the surface of the sun like this for a while, but at some point they do this and they erupt, which is quite spectacular. And sometimes when you get a filament eruption like this, you then get one of those coronal mass ejections as well. And again, filament or CMEs following filaments can cause some quite significant geomagnetic storms, but again, we tend to call them kind of moderate rather than the really big storms. The other thing that these coronal mass ejections can be related to is solar flares. So this really bright spot here is showing a solar flare. So solar flares are kind of a huge release of radiation, essentially. So we can measure it as X-ray flux. That's how we classify the flares. And you see it as a really bright light on the surface of the sun. And as a kind of general rule of thumb, the larger the flare, so X is the largest class of flare. They go A, B, C, M, X, for reasons that I've never actually quite found out why they skip so many letters. But anyway, X is the largest and it's an exponential scale. So each, step up your scale is significantly larger than the one before. And as a general rule of thumb, X-class flares tend to be related to faster and more damaging CMEs, but it's not a hard and fast rule for any of this. So then what happens is our coronal mass ejection heads out into space, and after some time, it hits the Earth's magnetosphere. So the fastest CME ever recorded was, I think, somewhere around 14 hours. The slowest are more like 5 to 6 days, or actually, it's very difficult to tell how slow they are, because once they're that slow, they have such little impact that we can't actually really register that they've arrived. And once the CME hits the Earth's magnetosphere, it squashes it even more on the sunward side, and you get lots and lots of energy gets into the Earth's magnetic field and all the different current systems that are kind of around the Earth. So that leads to increased electric currents, and that means the magnetic field becomes very, very variable. And as some of the solar particles also get into the system as well and follow magnetic field lines down towards the Earth. And the one factor that's really hard to tell up until the point that it hits is in this coronal mass ejection, if the magnetic field within it is pointing southwards, then when it arrives at the Earth, it connects with the magnetic field very well. And it's a bit like cracking open a window and just letting so much more energy into the system. Okay, so what do we actually measure in terms of why do we call it a geomagnetic storm? It's mostly because we measure the magnetic field routinely and that becomes highly variable. So this image here is a magnetogram from Estelmuir, which is our observatory in the Scottish borders. And this is for what we call a quiet day. So you can see so this top line is declination. So that's just angle from north, effectively. And then the horizontal intensity and the vertical intensity at the bottom. And you might not be able to read the numbers, but the horizontal intensity, for example, the kind of background level of it at this particular time was around 17,500 nanoteslas, and the vertical was around 46,000. And that largely comes from the Earth's core field. So the field generated in the outer core that controls our main magnetic field. But on top of that, there's a few other sources. So there's things like the crustal field, which is fairly static, so we don't really see it moving. But then there's also this, what we call solar quiet. So that's what causes this kind of curve. And we see this every day, pretty much the same, which has, a small range compared to the background field, but it's certainly a clear signal that we see all the time. On a disturbed day, however, we can no longer see our diurnal signal, our daily signal, because the rapid variations caused by the space weather kind of just overall that entirely. So you can see now the ranges have gone from kind of 20 nanoteslas on a quiet day to around 900 on this kind of stormy day. And you can see quite clearly here where the storm begins. This is called the sudden storm commencement, where there's a big deviation in the magnetic field, and then lots of kind of rapid high frequency variations and kind of big excursions from the background field. So that's our geomagnetic storm. The largest storm that we know of is the Carrington storm, which was in September 1859. And here are some magnetograms from the Greenwich Observatory, which was recording at the time. And you will notice that there are some gaps. And some of those gaps may have been issues with the recording, but some of them were definitely because, well, the pen went off the paper, pretty much. So we know it's a very big storm, but we don't actually know how big it was entirely. But we know it was a pretty huge event because there were aurora sightings recorded way down to kind of Cuba and Hawaii, which means that that auroral oval that normally sits over kind of Canada and Iceland had expanded a long way south from where it normally would. And I think one of the reports was that somebody in London was sat out reading their newspaper by the light of the Northern Lights, which, to be honest, I'd quite like to see, but it does have an impact on technology. So even in 1859, the technology of the day was quite badly affected, with telegraph systems sparking. Some failed, some started fires. Some of them, they disconnected all the batteries, but were still able to have a conversation. So you can imagine if that had that impact on the very limited technology of the day, a storm like that now would be very interesting to see what kind of happened. So why are geomagnetic storms a hazard? Well, they're not a hazard to humans directly, but it's that electric field that gets induced in the ground that can cause currents to flow in things like power networks, pipelines, railways, and some communication cables. And there have been some events which caused damage to transformers in power grids. I think this was from the March 1989 storm, which was quite famous because it wiped out a large part of the power system in Quebec, and that happened very quickly and took a long time to fully recover, which March in Quebec is a very cold time, so it's not ideal to leave people without heating for that long. And then just to kind of put it into the kind of wider context, so back in kind of 2011, 2012, the UK government started looking for any hazards that they maybe weren't aware of previously. So that was prompted by the volcano in Iceland that shut down UK airspace for quite a while. They said, oh, are there any other risks that maybe would have a huge impact on the UK? So space weather at that time got put on what's called the National Risk Register. So here's the National Risk Register for 2020. And you can see it has basically a whole list of different kind of things that might affect the UK, from things like crime and malicious attacks, as they're called, through all the different environmental hazards and other kind of accidents and things. So space weather is here, number 19. So it's considered a relatively high likelihood event of a severe space weather event happening. And that's, it's considered that it could happen up to 5 to 20 times in 500 years. And this level C is the amount of impact it would have. So that's kind of an indication that it would have a fairly significant impact, enough that people would be very aware that something was happening, but hopefully not so long lasting. So just to put it into context, 25 up here is a pandemic. And we're all quite aware of the impact that that's had. So this kind of top level is the biggest impact. So we're not quite there with space weather, which is probably a good thing, but certainly it is something that people would notice. Some of the challenges around space weather are that it is likely to have a global impact in much the same way as we've seen with the pandemic, and that there's a huge interdependence of potential impacts. So, as you've maybe got a sense of from that slide near the beginning where we talked about all the different effects of space weather. So, if you've maybe lost some power and you've got, local resilience forums trying to work out what's going on and sort people out, but you've also lost lots of your methods of communication, then that complicates the response. And there's also this thing that there's probably very little warning. So as I said before, the fastest CMEs tend to be the ones that are going to cause the biggest impacts. But that means that we really don't have very much time to prepare, especially when you consider, so that fastest one ever recorded was around 14 hours. It takes a couple of hours to get enough of that satellite data back to be able to see, firstly, that there's been a CME, and secondly, be able to actually get the kind of properties of it to put it into any models. And then the models that help you determine whether it's going to hit or whether it's going to miss or whether it's going to, and what time it might arrive, are very complex, and they take about kind of 6 hours to run. So you're talking about kind of 8 to 10 hours before you've even managed to model anything and decide what's likely to happen. So if it's only going to take 14 hours to arrive, that's not a lot of time. There's also uncertainty about the reasonable worst case scenario. So for a lot of natural hazards, there's a long geological record where you can go back and you can find lots of examples of big events in the past. Space weather and geomagnetic storms don't leave any record. So we only have kind of 150 or 200 years of magnetic measurements, and only for very specific places. So although we tend to use that Carrington storm as our worst case scenario, but as I said, even that storm, we don't actually know how big it was everywhere around the world. I think there's 1 or 2 observatories that were operating at the time where it actually didn't go off the scale. So they know more or less how big it got, but as soon as you get kind of to higher latitudes, well, mid to high latitudes, we really don't know how big it got. Okay, so I thought I'd talk a little bit about the research that I do at BGS, and that is mostly focused on what we call geomagnetically induced currents, so GIC in power networks. So as a little explainer onto how you get GIC, it starts with this varying electrical currents in the ionosphere. So because we've got a magnetic storm, you start to get these big current systems set up in the ionosphere. And that then generates a varying magnetic field in a perpendicular direction. And then that varying magnetic field induces a secondary electric field in the ground. And that electric field then causes currents to flow through the ground. And particularly in kind of resistive ground, currents like to find the easiest path, or the path of least resistance. And power grids are deliberately designed to be very low resistance, to be able to move lots of power around in the most efficient way. So what happens is GICs flow in and out through the grounded points of a power network. So they flow through the grounded point and then through the transformers and into the power lines. Now the power lines themselves can handle that, and that's not a problem. The real issue with GIC is it looks like a DC current, but transformers are designed to deal with AC current. So effectively what the GIC does is it just pushes the transformer out of how it normally operates. So most of the time that will look like things like what are called voltage instabilities. So basically the transformer starts to realize something's not quite stable because you're getting these weird extra currents, and that might trip kind of protective relays that are there for protecting the transformer from, you know, strange goings on, which most of the time is okay. But if you had a really big storm, what that might then do is to push the problem to other transformers, and then they trip and then they push the problem onto other transformers. And what can happen in the absolute worst case scenario is the transformer core heats up, and that's a very bad thing. And what can happen is then basically things fail spectacularly in a way that you then have to replace the transformer. And I don't know if you've ever looked very hard at transformers at substations, but they are not small bits of kit. They're very difficult to replace. So a lot of our work is around helping power companies to understand and to mitigate against space weather impacts. So to do that, we model the GIC in the power grid. So the first thing we need to do that is the magnetic field. So as I've already said, we measure the magnetic field. BGS has 3 permanent observatories in the UK. So one at Hartland down in Devon, one at Estelmere in the Scottish borders, and then Lerwick up in Shetland. But we also now have a small network of Raspberry Pi magnetometers, which are in schools around the country. And we've recently installed actually a couple more to do with our SWIGs and the swimmer work that you mentioned in the introduction. Alongside the magnetic field, you also need to know something about the conductivity of the ground, because in highly resistive areas, you're going to get more currents pushed into the power network. So to do that, we use the geology map of the UK to give us a conductance of the surface. And then we can combine those to get an electric field model of the induced electric field in the ground. And then alongside that, we also need a power network model. So this is a model of the UK transmission network. And that's something that we're working on improving at the moment. And then we can combine all of that and we can get what we call modeled GIC. So for example, in this map, this is an example from that 1989 storm that I mentioned where the power system in Quebec got knocked out. And each of these circles represents the excess current effectively flowing through a substation. Now, not to alarm anyone if you happen to live near any of these kind of big blobs, that doesn't mean that that much current is flowing through any one transformer. A lot of these sites have multiple transformers, so that current wouldn't be a problem. But it's important to create things like this so that we can go to National Grid and say, okay, this bit of your network might be more at risk, or another part, depending on the storm and the scenario. And then they can use that information to make sure that the grid is resilient in the event of a space weather event. Another area that we've started looking at as well is in pipelines. So high pressure gas transmission pipelines tend to be steel pipelines that are buried underground, and because they're buried, they're prone to corrosion. So to protect against that, they use something called galvanic protection, where you try and maintain a fairly specific potential between the ground and the pipe. But if you have a big geomagnetic storm going on, what can happen is that potential massively increases. Well, not necessarily massively, but it certainly is going to be affected by that geomagnetic storm happening. So we've recently created the first model of that for the UK. And you can see our early results show some fairly large potentials, so up to kind of 40 volts or more, suggesting that might really be a problem, and that might increase corrosion in the pipelines. Now, again, please don't go away saying, oh, there's 40 odd volts of potential difference, because this is a very early stage model and there are lots and lots of assumptions and things that we don't know about the network. But this is just allowing us to kind of start the conversation and be able to go away and say, there might be a problem in certain parts of the network, but we now need to refine that model. Okay, so the other thing that we do at PGS is space weather forecasting and providing kind of operational services for people like National Grid. In terms of trying to forecast the effects of space weather, it basically means lots of looking at the sun. So these images along the top here are all from the Solar Dynamic Observatory, which is a satellite between the Earth and the sun, which looks at the sun in lots of different wavelengths of light, because each of these different wavelengths lets you see something slightly different about the sun. And then this image here is very much the kind of image you would see if you took a telescope out in the garden and put a solar filter on it and looked at the sun. And then, some of these satellites also give us kind of magnetograms, so we can look at the magnetic field near the surface of the sun. And then these are the coronagraph images that I showed you before. And then we also measure the solar wind. So that's the Discover satellite, measures real-time solar wind and sends that back to Earth in real time. And then there are satellites like GOES, which are, I think, geostationary orbits, so they're orbiting the Earth all the time, and they measure the X-ray flux. So this tells us if there's been a solar flare, and it tells you quite quickly. There's also just an ever-growing suite of data and models available for forecasters and modelers and industry people to use to understand the space weather risk. So, for example, this on the right here is the European Space Agency's Space Weather Service Network portal. So there's now tons of new products on there from people all around Europe and beyond, with different things like actually trying to forecast the solar wind or forecasting magnetic fields on the ground. And then there's models like this NLO model, which is the one where you can put in coronal mass ejection. So this is the sun here, and the Earth is the little green dot. You can model a coronal mass ejection moving out through space, and that gives you an idea of whether that coronal mass ejection will hit the Earth or how much of it will hit the Earth. But these are complicated models that take a long time to run. So it's really helping with forecasting, but there are still a few problems. So we're quite a long way behind, say, terrestrial weather forecasting, and even they don't get it right all the time. And that's partly because there are limited data. So almost all of our data comes either from the Earth itself or from the satellites that are between the sun and the Earth at what's called the L1 point. So that's where it's kind of gravitationally stable between the Earth and the sun. So it's quite low cost to keep a satellite there. There are a few other options. So the A and B on here are what called the stereo satellites. So stereo A started at the Earth and it went ahead of the Earth in its orbit and it's come all the way around. And stereo B went the other way, it's called stereo behind. Unfortunately, we've lost contact with stereo behind now. But stereo A, where it is at the moment, is actually really useful because it firstly gives you a view of what's coming on the sun's surface round to face the Earth, because the sun rotates kind of that way. But it also means that if there is a CME released from the sun, it gives you just that extra angle to see whether that CME was actually heading, you know, off that way, or if it's heading off this way, you know, if it looks like it's just heading out to the side from the Earth. ESA are planning to launch a new satellite to more or less where the stereo A is, and that will be fantastically useful when it comes. But otherwise, all these other kind of satellites are all science missions, so they were never intended to support kind of operational space weather forecasting. They don't necessarily send data back in a timely manner. And then, as I've already mentioned, the fastest CMEs are generally the most damaging, so you get the least warning. And lots of the forecasts that we use at the moment are based on that solar wind data once it's already arrived at the L1 point. So we only really get kind of an hour ahead, or even less sometimes, to know what's going to happen at the ground. Having said all that, we still forge ahead and do our forecasts. So at BGS, we issue a forecast every weekday, which we make available to the public on our website or through our Twitter. And we also talk to the Met Office every day as part of that forecast to make sure we're giving a consistent message. And then the other thing that we do is we issue disturbance alerts. So if we think there's going to be a good showing of aurora or a big storm, we put out an alert, which again is available to the public, but we also obviously send it to all of our kind of customers and industry users to make sure that they know something is coming. And as I've already mentioned, we do a lot of work for National Grid and for the Met Office, and we provide lots of kind of real-time data and monitoring both for them and to the ESA Space Weather Network portal, which I think is available for anyone to sign up to. And being the geomagnetism group at BGS, that data is mostly from us, geomagnetic observatory data. There's some electric field data, and then things like geomagnetic indices and index forecasts, and some alerts as well. Where possible, we also make our data available to the public. So this is our kind of public space weather page, which gives a kind of very simple indication of the current activity based on the KP index, or a real-time version of the KP index, but you can also click through and get more plots of activity should you wish. And yeah, that's kind of all I was going to say. So just to summarize, space weather can have wide-ranging impacts on technology. We're working all the time on trying to obviously mitigate those impacts, but there's new types of technology coming on the market all the time as well. So it's making sure that anyone who's developing things is aware of the risk of space weather. And that can be quite hard because it's not something that we've really seen a big impact on. So it can be difficult to get industry users to kind of pay attention to the risk when they've never had to think about it before. The effects of space weather are global and can affect lots of different things at once, which could complicate issues. And our modelling of the geoelectric field, induced currents and pipe soil potentials are helping us to understand the risk, but also helping us to help end users to actually mitigate the risk as well. And part of that is that forecasting space weather is going to be key to reducing the impacts. The more accurate your forecasts are, then the less it costs people to either react or not react, depending on the circumstances. And forecasting is improving all the time, and it's being taken more and more seriously. And we're starting to see a bit more money at kind of national government level being put into forecasting space weather, but there's still lots of challenges. So yeah, thank you very much for inviting me to talk to you today. Any questions?
Well, thank you very much for that. I'll start with one question, which was way back at the start of your presentation. You mentioned that solar events hitting the top of the atmosphere and creating changes in what I think they're the ring currents up there, that can actually interfere with the downlink from satellites. Mm-hmm. And I wondered, did I understand that correctly? And I wondered what the mechanism was. Is it sort of Faraday rotation or something like that? The other thing was I seen a figure for the Carrington event of an estimate of X42. I don't know if whether that sounds familiar to you, but anyway.
Yeah, so I have to admit my understanding of the impacts on satellites is relatively limited, but a lot of what happens is so that in the ionosphere, basically it gets very, very disturbed, and that's kind of the region where you get the aurora visible, because you're getting lots of collisions between charged particles and you're getting current systems set up. So all of that just kind of acts to interfere with signals that are trying to pass through. That's a very vague explanation, I realise. In terms of the Carrington event, yeah, I've seen lots of different estimates of kind of the size of the solar flare. I can't think of any of the ones I've heard off the top of my head, but I guess X42 is possible. We've certainly, I think since we've had kind of measurements in the way that we now measure the size of solar flares, there's been an X20. So it's, I mean, an X42 would be significantly larger because it's an exponential scale, but yeah, who knows?
I've got a question. Is there any data that allowing you to test your models against what actually happens in the power system? That would be an obvious thing to have done, or the next steps. And is the power industry really engaged with this, or is this just something that's happening around them which they feel they can ignore?
Yes, I'll come back to that. So in terms of data, we have a small amount of fairly limited data for the UK grid that we can compare our models to, but it's quite limited and it's not the best quality. But we've recently started making our own measurements in a, we use what's called the differential magnetometer method. So in fact, I think I've got a slide on that. Yes, so basically, oh, I've not got the slide. I thought I had, that's annoying. Okay, so basically you plonk one magnetometer underneath the line and one at a distance, and you measure the difference between the two, and you assume that they're close enough that the magnetic field, the kind of regional magnetic field, should be the same. So you assume any difference between them should be caused by GRC in the line. And that gives you a kind of remote measurement of GRC in the line. So that's something we can do ourselves. And we've started doing that. And we've recently published a paper on our kind of early findings from that method. But yes, it's something that we're trying to do more of. And because we recognize we really need to be actually validating these models. It's no good creating a model and saying, oh, that's what's happening, when it might not be. In New Zealand, they have something like, oh, what is it? I think it's 24 substations. They have measurements of GIC in the oh, where do they measure it? I don't think it's in the trend. Yes, actually in each individual transformer.
in the earth pointer transformer.
Yes. Yeah, our partners in New Zealand are incredibly well endowed in terms of data, in terms of GIC data. The problem they have is there's very limited magnetic data to make the model good, like that you're putting in to then get the GIC out. So it's a challenge either way, but yeah, they're doing some amazing things now, because they're Transpower, who control the power network in New Zealand, are completely on board with this, are really, really interested, and are very involved in the project. They're really helping them to get, detailed information about the grid and all of these wonderful measurements, and helping them to improve it each way. And they're interested in all the different scenarios. That, however, is not the case in most of the rest of the world. In the UK, say National Grid are fairly on board with this. They've certainly been involved. Like, we've been working with them for around 20 years, I think. So they are aware that this is a problem, but they also consider that the grid is resilient enough that it's not really a problem. So they're not too concerned about it. Other countries, it's starting, I think national governments are now starting to recognize this and push a bit harder. So they're having to start to pay attention. But yeah, in the past, it has been a little bit of a kind of, and understandably so, a big storm that's going to knock trees into power lines and things is much more likely to happen much more often. So that's the kind of risk that they're very occupied with, which makes sense, other than this, when you've got this scientist waltzing in saying, oh, this thing that you can't see and you've never experienced might affect your power grid. It's understandable, but I say in the UK it's well recognized. So hopefully, should a really big event happen, we can all go out and look at the Northern Lights and not worry about anything else too much. Although, of course, if the power went out, it'd be easier to see the Northern Lights. But
I think it's always regarded that the Quebec event was due to the unique configuration of the Quebec grid, rather than anything that's directly transferable to the UK. Therefore, we can ignore it, which is a bit head in the sand. But hey.
But yeah, I mean, that there is a little bit of truth in that. There's the way that the grid was configured did play a part, and the way that the UK grid is configured is likely to actually help it be resilient. But yes, obviously I would like them to take it very seriously so that they fund lots of my work. But
or move to New Zealand.
All that, yeah.
Thank you.
It was a very interesting talk, Gemma. I really enjoyed it. There's been a lot of talk that there's going to be a big CME and it's going to knock all the power lines out and things. Is there any fact in that? We've probably got no history of it, have we?
No. So as I said, one of the issues we have is that we don't really know how big an event could be, and we don't really know how often they happen. And we now have around, I think it's 150 to 200 years worth of data, but obviously the early data is kind of limited. But yeah, beyond that, so we don't know whether the fact that we've not had any kind of huge events since 1859 is luck, or whether it's because they really don't happen that often. In terms of, so there is a kind of thing of the solar cycle. So the solar cycle is an 11-year cycle where you get a maximum and a minimum every 11 years. And the last two, I think, solar cycles have been relatively small compared to previous ones. But the kind of big event that we might get doesn't necessarily have to happen at, a high point in the solar cycle. It could happen at any time. So yeah, it's really hard to know. I think if you ask most scientists, is there going to be a really big event next year, they'll go, I don't know, maybe.
We've only got experience. We're like, from the sun's point of view, we're a tiny little spot in the universe. There's 4 pi radians that you can get these bursts going. So
Yes.
the probability is quite low that it's coming our direction anyway.
Yeah, so there was one back in, when was it? 2016, I think, that there was a really big CME that left the sun, and it hit one of those stereo satellites, but it didn't hit the Earth. And there's a fairly big school of thought that, if that had hit the Earth, it would have been quite a big event. Not as big as it could be, because the magnetic field within it was mostly pointing northwards. But yes, so we could get, a huge CME and it completely misses. And that's, another part of the fun of trying to forecast what's going to happen and when.
Gemma, there's a couple of questions on the chat line. I'll just pick them up. The first one I've got was from Richard, when relating to the map of the UK event in the 1980s, and there was a notable symmetry between the minus sort of 50 amp difference in the east and the 50 amp positive in the west, or the other way around. And a question about whether why the symmetry, given that the pipe network doesn't have the same symmetry.
So in the power network, it's because of the way it's all connected, basically. So effectively, the GIC flows into the grid on one side of the country and out of the grid on the other, because the current systems that are creating that effect, particularly at this moment of the storm, tend to flow east-west. So you get east-west currents in the ionosphere, which translates to east-west currents in the ground. So they predominantly flow into the power grid on one side of the country and out again on the other side of the country. In the pipeline network, you don't see that in the same way, because pipelines are grounded continuously. So in pipelines, the symmetry is for an individual pipe. You get positive at one end and negative at the other for each section of pipe that's not separate from the rest of the grid. So each section of pipe is kind of its own separate piece of infrastructure, whereas in the power grid it's all connected. Hopefully that explains it.
There's a question from Kevin, whether there's any more information about the Raspberry Pi sensors. People always get switched on when Raspberry Pis get into the conversation for sort of citizen science. Are they, I assume they're not expensive, but are they easily available?
Yes, so I think the ones that we did for the schools, there's a page about it on our website, but I think they were around maybe £200 all in, but you can actually do it cheaper than that or much more expensive than that, depending on the sensors that you buy. So you can buy magnetometers fairly easily for Raspberry Pis now, and yeah, as with anything, there's a range in how expensive you want to go with that. But yeah, they're pretty cheap. They had to be, because we were doing it for schools, and schools famously don't have a lot of money. But I think on our website you can actually get the instructions on how to do it.
Yes, I know we've got a poster session on a Raspberry Pi magnetic sensor. So as part of our RAG 21 in a couple of weeks, so that'll be of interest. There's one that's testing your knowledge of semiconductor devices, you'll be delighted to know.
Ooh.
Talk of gas-filled tubes that handle both high current and high voltage, so known as silicon avalanche suppressor diodes, and other switching methods which can be used to bypass these dangerous induced currents. Is there work ongoing, do you know, in these sort of devices?
I think some parts of the world have decided they're a good idea. Some haven't. I think the jury is still out. One of the issues is if you bypass it in bits of the grid, but not others, you actually just push the problem onto the other bits of the grid. So yeah, I think for them to work, you'd actually have to install them on absolutely every single transformer or whichever bit they get connected to. It's not something I know a huge amount about, but yeah, I think the jury's still out a little bit on whether they're worth the expense or whether they actually help. Because I think it is quite expensive to do it, but I'm not entirely sure.
Is anyone looking at capturing the energy and storing it and giving us a bit more green energy?
Not as far as I know. It's not really, it doesn't really produce that much, and it's so sporadic and unpredictable that I don't think it's really worthwhile. I'm sure somebody somewhere has decided that it's a good idea and is doing it, but it's not something I've heard about. Yeah, I'm not sure it would really add very much.
Any other? Sorry, go on.
So I was just clearing my throat, sorry.
All right, okay. Any other questions?
Yes.
Go, Norman.
Oh, you're muted. No.
You're muted. You're muted, Norman. I'll see if I can unmute you, Norman. We can't hear a word.
Right, you should be able to hear me now.
Yes.
Go ahead.
There are many different types of magnetic sensors, but I'll stick to the ones that's within the realms of amateur observers. Magnetoresistive sensors, proton precession, and the flux gate. And I note the BGS magnetometer uses 3 flux gate sensors. Do you, as a researcher, have any preference to the type of magnetic sensor? Or is it down to the electronics and the processing?
So it depends exactly what you want to measure. So we actually use both flux gates and proton precession magnetometers, because the flux gates are very good at giving you the variation in the magnetic field. And I'm trying desperately to think back to my university days of exactly how these work. But I think the proton ones tend to be better at giving you that absolute value. So we use a combination of the two and use absolute measurements to give you the kind of baseline, and then the flux gates give you the variations on top of that. I think that's correct. And the technicians at BGS will kill me if I've got that wrong. I think a lot of it depends on, again, how it's a kind of cost versus accuracy versus how regularly you want to take measurements, and all those kind of different factors.
The other question I'd like to ask is there any value in putting two probes in the ground, maybe 10 or 50 meters apart, and looking at the voltage or the current flowing?
Yes, and
Or is this just noise?
we do actually do more or less that at our observatories now. We measure the geoelectric field. So we have exactly that. It's two probes spaced around 100 meters apart, one north-south, one east-west. There's a few things you have to, so you have to use like a non-polarizing probe in a Weezer. I think we were using a copper sulfate solution, but I think that might have changed. But basically to stop polarization with the ground, because otherwise you do just measure noise. But that is giving us good measurements of the electric field now at our observatories, and we're trying to do that in a kind of long-term basis, which turns out is quite hard because things degrade quite a lot if you leave them stuck in the ground. But there are a few places around the world that have been doing it for a long time as well. So they're really useful kind of additional measurements, and you can certainly see the kind of geomagnetic storm happening and inducing those electric fields.
Something to think about. Thank you.
Okay. Gemma, could you unshare your screen?
Yes, certainly. Oh, where's it gone?
Can I just say thank you very much? Excellent talk.
Yes, indeed. I was going to say exactly that, and I'm sure that everybody will reciprocate. Thank you very much for a very informative talk, definitely, and very grateful for you sharing your evening like this.
Okay, thank you very much for having me. It's nice to talk to some different people.
Strange people, as my niece tells me, but there we go. Okay, excellent. Do we have any sort of mini poster sessions on radio astronomy stuff? Any announcements or whatever? Paul normally solicits additional information if anyone's got anything to show, but wonder if we've got anything this evening. Somehow I didn't think that was going to be the case, but anyway. Well, thanks to everybody for attending then. The next event in the RAG series is I don't know whether it's episode 3 or episode 4 of Rupert Powell's Python workshop, which is a week tomorrow. And then the following Saturday, as I've mentioned before, we've got the RAG 21 one-day event. So I hope people will find the time to do that. Unfortunately, it's still going to be Zoom, unlike the pictures on the right-hand side here, where we actually got to have proper meetups. So hopefully 2022 we'll be able to return to that start of events, and it would be nice to meet up some of the faces that have just been peering out from the screen here. So thank you very much, and good evening, everyone.
Could I have a last question, Paul?
Well, Gemma wasn't quick enough to run off, so yes.
Gemma, the Citizen Science Project, could you give us a point or even just an email later, somebody who would be willing to talk to citizens about their Citizen Science Project and perhaps answer some technical questions?
You're muted.
I've just put a link in the chat to our website.
Aha.
At the bottom of that is a contact for my colleague Kieran, who was the one kind of who really drove that project.
Thank you.
So hopefully that will give you a bit more information.
Yes, we'll freely tell him you set him up.
Yes, well, he set me up in the past, so it's fine.
A quick comment to thank you, Gemma. But at our conference, I'm giving a talk on Schumann resonance, or rather a presentation. And I've been in discussions with Kieran over the last few weeks.
Yes, I was about to say, I bet you've talked to Kieran then, because he's quite involved in Schumann resonance work.
Yes, he's been very helpful over the years. One day I hope to meet him. Anyway, thank you all, and I hope you'll see me in a couple of weeks.
Yes, thank you. And thank you, Norman. I can tell him if he wants, you can have an extra 5 minutes for your talk.
Oh. I'll be able to
Right,
pause
I
a bit
think that-
longer.
Okay, thank you, Paul. Good night, everybody.
Good night.
Good night.
Thank you, Paul. Good night, and thank
Good
you,
night.
Gemma.
Good night. Bye now.
Goodbye.
Bye bye.